Greetings, stargazers, and welcome to the March General Meeting of the Kalamazoo Astronomical Society. I want to thank everyone for joining us on Zoom. March 1st, of course, was the first day of meteorological spring, and it shows in the weather outside because just for historical perspective here, because you all know this, but for people watching on maybe YouTube years later, we are currently under a winter storm warning and the roads are treacherous out there. So we have a long-standing policy. We prefer our members not die to or from or at a KAS event. So we're lucky enough that we can gather on Zoom. And I'm lucky enough to have internet again after 5.5 days without during the great ice storm we got last week. So I'm going to rearrange the agenda here since we're on Zoom. I'm going to go to Zoom format, which means we're going to jump right into the speaker here. So tonight's featured speaker is a professor of astronomy at Western Michigan University and has been a Kalamazoo Astronomical Society member since 1997. He received a bachelor's degree in astronomy from the University of Illinois in 1985 and a PhD in astronomy from the Ohio State University in 1990. He performed doctoral work at the Carnegie Observatories, Space Telescope Science Institute, and the University of Kentucky. His primary research interests are spectroscopic analysis of active galaxies and quasars, and the interpretation of these spectra through numerical computer simulations. He may have added a few things since he first sent me his bio years ago, but that's the nuts and bolts of it. And I'm sorry, one thing I didn't quite have time for is to figure out what number presentation this is for him. I mentioned last month Sinclair just gave his 16th talk. For Kirk, it's got to be around a dozen at least. So returning once again, Dr. Kirk Korista. Take it away, Kirk.
Hi, everyone. I'm going to share my screen. Ready for that, Richard?
Go ahead.
Okay. All right, so tonight I'm going to give a presentation on the some of the astronomical findings of Sir Arthur Stanley Eddington. And I have subtitled as "With Stars in His Eyes," and we'll see why that is as we go through the presentation. Up here in the upper right-hand corner, I have a nice little quote here where he's musing about the possibilities of being able to figure out, becoming competent enough to understand something so simple as a star. So we'll start out with his childhood. He's born Arthur Stanley, end of December of 1882, in the northwest of England. And he was a son of Quaker parents, Arthur Henry Eddington, who was headmaster at the local Quaker school, and his mother, Sarah Ann Shout. His younger brother to the older sister, Winifred. But his father died when he was young, only a couple of years old, less than two, in the typhoid epidemic of 1884. And Stanley, as both Winifred and his mother called him, moved in with his paternal grandmother. And this was in the southwest of England, in a town called Weston-super-Mare. The house actually had a name called Varzin, which has an address at 42 Wallascott Road, and it's someplace you can actually visit today. It has a nice plaque honoring Arthur as his childhood home. Before he could read, he tried counting the words in the Bible, and on numerous occasions the stars in the sky, and he knew his timetables to 24 by 24. And of course, is the Count from Sesame Street, who likes to count. He obtained a 3-inch telescope at about age 10, which sparked his lifelong study of the cosmos. And I'm sorry about the nature of the presentation. Normally I'm facing an audience rather than my screen, so you'll have to bear with me. Hopefully it's okay with everyone. He was initially homeschooled by his mother, but by age 11 or so, he entered a primary school, Bryn Mawr School, where he was there for 5 years. And precociously, at age 16, he entered Owens College in Manchester on a scholarship, where he excelled in mathematics and English literature. And it turns out that both of these figure prominently in Arthur's future career. You might have guessed mathematics did, but it turns out actually he was also well known for his knowledge of English literature. His important mentors at Owens, two of them anyway, one was Horace Lamb, who wrote famous textbooks on hydrodynamics and sound, and Arthur Schuster, a physicist known for his early work on radiative energy transfer in the atmospheres of stars to try to explain the presence of absorption lines in their spectra. And we'll see that both of these come back to Arthur's story later on. And finally, in 1902, he entered Trinity College of Cambridge University, again on a scholarship, where he studied mathematics, physics, and astronomy. So I'm going to take a slight diversion here. Before going on to his astronomical career, I wanted to bring up something which was very important to his upcoming career, because it involved a decade-long, at least, series of clashes and debates with a giant of science at the time. And it was Sir James Jeans. Stanley, as I'll sometimes refer to him, drove his detractors, and there were several, who practiced the traditional incrementalist mathematical approach to the scientific method based upon certainty and completeness. And so the primary giant at the time in this camp was Sir James Jeans, mathematician and astronomer and physicist. But his approach to things drove them to distraction. Because Eddington, instead of this incrementalist mathematical approach, relied on his physical intuition, his remarkable ability to simplify while retaining the essential elements. And his approach really was with stars in his eyes, an optimism of science, to take a leap of exploration from solid ground, where we understand things really well, into terra incognita to ask, what if? And this is the part that drove Sir James Jeans to distraction. Because his approach was, as I said, very incrementalist. We stand where we know, and we make advances very slowly, incrementally, as we gain little bits of knowledge. And we shouldn't be even talking about things we supposedly don't have any information about. So there's a whole series of debates, written and spoken, that ensued. There were withering, sharp criticisms from Jeans aimed at Eddington. Eddington, of course, was a junior, and so his responses remained polite and deferential, but he still held up his end of the argument. And the primary argument he had for his approach was that his phenomenological approach opened up new avenues of investigation to astronomy that otherwise remain closed while we're waiting around figuring out how things work. With solid certainty. So the discovery of Cepheid variable stars in the early part of the 20th century sets Arthur on the path towards understanding the luminosity of stars. These are we learned, because back then all we know that these were objects that stars that varied in their brightness. We didn't know why they varied in their brightness, but they were also noticed by, I think it was Miss Leavitt, that there seemed to be a relationship between the period of variation of their brightness with their luminosity. And so Arthur decided to try to understand these objects. And so this is his first venture into the study of stars. He was likely inspired by his former tutor, Lamb, and eventually who worked on hydrodynamics and sound waves, and eventually proposes the first and nearly correct physical model for the pulsation and their sizes to explain their brightness variability. Next, so this is right around 1916, 1917, he proposed a simple mechanism to describe, okay, this is a little fancy here, anisotropic, which means preferred directions in energy flow by radiation in the atmospheres of stars. Instead of assuming that the radiation flows equally in all directions, which we knew was not going to explain what's going on in stars, he came up with a simple mechanism to describe the fact that the flow is not completely isotropic, but is preferred in some directions. And ever since this time, it's been called the Eddington approximation, and it's still used today in modern day studies of planetary atmospheres as well as stellar atmospheres. And it's a very useful average over complexity. And this is one of the key strengths of Eddington, his ability to get past the complexity and do something useful. Then following up on the work by Schuster, his other tutor at Owens College, and Carl Schwarzschild of the black hole fame, he applies his approximation to predict the change in temperature with depth within the star's surface layers. And in doing so, you can explain what's appears here in the left-hand, the right-hand side of the slide. Shows an image of our sun. And you can see that, of course, anyone who's looked at the sun through a nice filter, neutral density filter, will notice that the center of the sun's disk always appears brightest. And then there's a very gentle gradation of intensity going down as we go further out towards the edge. And then it appears dimmest along the edge. And this is called limb darkening. And for a while, we didn't know where this came from. But in being able to use his approximation in a useful manner, he could determine the approximate temperature structure within the surface layers of the sun, and in doing so, actually explain to high accuracy this behavior of the intensity and the disk of the sun. And then in working with other scientists, Milne and Barbier, he also used this approximation to determine the strengths of a star's spectral absorption lines. By 1917, we had reasonably good measures of the star's outer characteristics, such as how far away are they, their measurements of mass, measurements of their surface temperatures, their luminous power, luminosities, and their sizes. That their surfaces were composed of gas, that was known, but the elemental compositions of stars was debated. And very little was known about what went on inside. For example, the state of the interiors was a huge mystery. We didn't know whether the interiors were in a gaseous state, liquid state, solid state. And we didn't know how energy was transported through the star. Convection, radiation, conduction. We also knew that stars were in a state of force balance. This is the net outward pressure exerted by matter balances against the inward pull of gravity within every layer within the star. And this was known to be in place because if there were any force imbalances present, the star would undergo dramatic changes in structure in a matter of typically minutes. Very quick anyway. Two physicists in the 19th century, late 19th century, Kelvin and Helmholtz, argued correctly that in lieu of some then unknown internal energy source, a star will slowly contract in the face of losing energy through their luminosity. So, for example, our sun loses has a luminosity of 3.8 10 to the 26 watts. So it means every second, 3.8 10 to the 26 joules leaves the sun in the form of light, and likewise for all other stars. And if our sun didn't have an energy source somewhere down inside, it would be undergoing this Kelvin and Helmholtz contraction. But by 1917, this contraction hypothesis was in grave doubt because the resulting energy imbalance timescale, that is, the star is losing energy, but there's no source of energy on the inside. That timescale for contraction for stars, which was estimated to be somewhere 100,000 to 100 million, depending on the mass of the star, mass and radius and luminosity of the star, were found to be too short in comparison to other interesting timescales. And it was at this point that Stanley was ready to take a leap into the stars. This is a quote from Stanley. The contraction hypothesis is an unburied corpse, referring to the last topic we were just talking about. He initially presumed something akin to energy given off in radioactive decay or matter annihilation into energy through Einstein's famous E equals mc squared. Something was balancing against the energy lost per second in the star's luminosity. And of course, I think even by the late 19th century, that it already ruled out any possibility of there being energy from chemical reactions. And then in 1920, Francis Aston found that the helium nucleus had 0.7% less mass than 4 hydrogen nuclei. And this was before we knew about neutrons. The exact makeup of the helium nucleus, other than its mass, was we could measure its mass. And we found that the 4 hydrogen nuclei had, summed up together, had more mass than the helium nucleus that presumably make up helium. And with that mass deficit, that of course excited Arthur. He thought for sure that this must be what's powering stars in terms of their energy source and allowing them to be in energy balance. In that 0.7% less mass in the helium nucleus is energy that through E equals mc squared can be thrown out exothermically in such a fusion reaction of combining hydrogen into helium. And so he envisioned some kind of process that involved the fusion of hydrogen and helium that at a rate that would be temperature sensitive. And this was way out ahead of everyone. And certainly was actually 20 years out ahead of figuring out how it actually happens physically. Now, he didn't know how it happened, but he's pretty darn certain it was going on inside of stars. This is a nice, in his address to the British Association in Cardiff in 1920, he said that a star is drawing on some vast reservoir of energy by means unknown to us. This reservoir can scarcely be other than the subatomic energy, which it is known exists abundantly in all matter. We sometimes dream that man will one day learn how to release it and use it for his service. The store is well nigh inexhaustible, if only it could be tapped. There is sufficient in the sun to maintain its output of heat for 15 billion years. I think in other versions of this quote, he also mentions that it also could lead to mankind's suicide, of course, referring to thermonuclear weapons, which weren't invented for another 40 years. So in Eddington's exploration of the workings of stars, he decided to start with giant stars, as well, they were known to be stars that had very large radii, so their average densities were low. And so it was thought most likely that something like the ideal gas would describe the state of the matter in the interior of the star. And such a gas exerts a pressure that's proportional to the density of the gas, that's the Greek letter rho there, in product with the temperature, and in ratio to the mean mass per particle, which depends on the composition. Now, the unknown composition of stars in the first couple of decades of the 20th century remained a kind of an empty spot in his development of the model of a star. It remained a parameter that needed some filling in. And let's see. I'll mention it later on. I won't spill the beans right now. Now, as far as mechanisms to transport energy inside the star, Schwarzschild had informed Arthur that that convection requires very special conditions, and so that didn't seem like a promising pathway for pursuing understanding stars. And so he decided to extend his model for radiation transfer of energy in the star's surface layers into the interior of the star, whereby energy gradually diffuses downhill in temperature from high to low radiation pressure. And that radiation pressure scales as temperature to the fourth power. This, of course, means that higher temperature gases emit more photons with greater energy and so exert greater pressures. Now, in this slide and one or two others, I am going to present some equations and some relationships. If those are uninteresting to you, that's fine. I will try to give an English translation to everything I present in equation form. So don't worry about the mathematics. So he assumed that there is pressure in the star that's supporting against the force of gravity, that it consisted of that from the gas, which he assumed to be that of the ideal gas, and that from the photons, P radiation. And then there's a simple beta, which is the ratio of the gas pressure to the total pressure. And therefore, since gas and radiation are the only two forms of pressure, then 1 minus beta, that fraction, 1 minus that fraction must be the radiation contribution to the total pressure. And with that recipe for pressure, and then the condition of pressure-gravity force balance, he found the following relationship between the interior temperature and density of the gas within a star of a given mass, and mean mass per particle mu, which again depends on the composition of the star. And you can see that the temperature scales as roughly a factor, remember, like 5 million kelvins, which scales directly as the mass of the star relative to the mass of the sun to the 2/3 power. And then you see at the very end there, it depends on the density of the gas within the star to the 1/3 power. All right, so setting all that aside, let's translate that a bit and say, so at a fixed value in gas density, more massive stars are hotter. And I want to make a point here that Eddington understood back then, and we still understand today. Stars are not hot because of, nor do they owe their pressures from fusion, okay, which is something that has somehow crept into introductory education in astronomy. Then Eddington took another leap to presume that the ratio, which we'll call R, of the radiation pressure to gas pressure within the star and the composition so the elemental composition within the star don't change within a star of a given mass. So you can see all of these leaps that he's taking here. So the ideal gas law, he prescribes a recipe for pressure. He presumes that the ratio of radiation to gas pressure and the composition don't change. These are all things we did not know. And at that time, had no way of directly determining. But he's saying, well, what if they are true? What are the implications? And of course, this is what, as I said, drove Sir James Jeans to distraction, as an example. But we put those together, then that resulted in a nice relationship between the star's mass and this ratio, P radiation to P gas. So you pick any ratio. It could be 10 to the minus 3, or 10 to the minus 2, or 0.5. Pick your favorite ratio of radiation pressure to gas pressure. And if that quantity is fixed within the star, then you can actually predict the mass of the star. And This is exactly what he did. And we can see that the star's mass scales upward with increasing values in radiation to gas pressure, meaning more massive stars have larger ratios of radiation pressure to gas pressure, and just the opposite. Lower mass stars have lower ratios of radiation to gas pressure. And that relationship is shown in this graph here. I plot on the vertical axis the mass of the star in units of the mass of the sun, and it's on a decade scale. So 1% at the bottom, then 10% going up, then 1, which is the same mass as our sun, and so on going up on the left side vertical scale. And along the bottom, on the x-axis, is the ratio between the pressure of the radiation in the star to the gas pressure inside the star. And there's a vertical dashed line marking the position where P radiation equals P gas. And everything we talked about up to now has become known as Eddington's standard model of stars. That's not something he named himself. It's just was named subsequently in history. I want to point out that for a star of our sun's mass, that this ratio of radiation and gas pressure is about 1 part in 2,000. And it reaches maybe 10% for stars of 18 or thereabouts solar masses. So gas pressure, just the regular thermal gas pressure, dominates the total pressure in nearly almost all stars, except the most massive ones. So one of his goals here for his exploration of stars was to be able to predict their luminosities. So here we are going on the next step. So remember, he assumed that the energy in the star is transported downhill in temperature from high radiation pressure at the center of the star to lower radiation pressure towards the outside of the star, from high temperature to low temperature, by radiative diffusion. Photons being absorbed, emitted, scattered again and again and again, and the energy slowly leaking its way out through the star. And you see that I spelled the word leaks out that way on purpose, because this is a very slow, gradual process. In our sun, this time scale is roughly 150,000 years. And it's a different number for different kinds of stars, but I just want to give you an idea that it's a very slow process. And you can also derive an expression for the star's luminosity from that. And a form of that, a simpler form of that, looks like the following. The star's luminosity is equal to the total energy, the ratio of the total energy of photons in the star in proportion to the time scale over which the energy of the photons diffuses through the star's interior. And this diffusion process is much like that which takes place when someone spritz some perfume in the corner of the room, and very slowly over time, the aroma of the perfume fills the entire room uniformly. But it's a very slow process. And then once that energy of diffusion reaches the surface of the star, it simply streams away at the speed of light, the star's luminosity going out into the cosmos. Oops. This relationship then can be expressed in the following equation, that the star's luminosity in comparison to our sun's luminosity is a number of like factor of 40, multiplied by the ratio of the star's mass to our sun's mass to the third power, with some little correction factors there having to do with, remember, mu is related to the mean mass per particle, which depends on the composition of the gas. And beta is the ratio of, remember, gas pressure to total pressure. And there's one more parameter that appears here, and that's Greek letter kappa. And this is the average radiative opacity of the gas in the star. And the opacity is a measure of matter's ability to interact with photons of light, either through scattering or absorption. So something that has a high gas that has a high opacity strongly interacts with light. Something with low opacity more weakly interacts with light. The opposite of something that's very opaque is something that's transparent, and vice versa. All right, so that's the basic idea behind opacity. And you see it appears in the denominator here. So a larger opacity means, all else being equal, the star will have a lower luminosity. And that should make some sense because the opacity opposes the flow of energy flow by radiation through the star. On the other hand, you can see there's a very strong dependence in the star's luminosity with its mass. Star's mass, it scales roughly as a cube of the star's mass. This quantity opacity is smaller for gases of higher temperature and smaller density. And these are the conditions found in stars of greater mass. And so the net effect is more massive stars more efficiently leak out their greater stores of luminous energy. And very simply, more massive stars are more luminous. What you're seeing here is a plot that actually appears in Arthur Eddington's 1924 publication in the monthly notices of the Royal Astronomical Society, noted there at the bottom. This is actually figure 1 in that paper. The actual numbers along the axes don't matter for our purposes here, but I'll describe what the axes are. The vertical axis is the measure of the luminosity of the star. It's a logarithm, proportional logarithm of that quantity. And along the horizontal axis is the logarithm of the mass of the star. So we're plotting luminosity versus mass, and we can forget about logarithms if that's not your thing. That's okay. All right. And the dots and circles and triangles and so on, these were measurements from the day. And Arthur had culled through measurements and found only the first and second class, in other words, the better measurements and estimates of stars' masses and luminosities that he included in this study. So those are the dots and crosses in circles and so on in that diagram. The curved line is his model. And one of the quotes from the conclusion of the paper was that, while I'm unable to find an absolute form of the relationship between luminosity and mass, the form of the law seems to be fixed within narrow limits. And so it would be surprising if the accordance shown in this figure arose from mere accident. And of course, you can bet that Sir James Jeans was all over him about this, because he didn't have a absolute measurement. Our understanding of opacity was rather crude in those early days. We only had some very broad estimates. We didn't know yet what the composition was of stars, so we didn't know what the value of mu was, the mean mass per particle. There were those who thought stars were made out of iron and calcium, and others who thought they were made out of hydrogen and helium, and it was just a big free-for-all for a while. That problem was solved in 1925. Well, at least initially in 1925 by Cecilia Payne in her PhD thesis, where she demonstrated for the first time that, based upon the spectra of stars and their absorption lines, that stars are mostly made out of hydrogen and helium and a small amount of the heavy elements. But her work was not readily accepted initially. And in fact, her advisor advised her to insert a sentence in her dissertation that is probably wrong. But she was right. But it took about 5 years before the overwhelming weight of evidence convinced everybody else in the field. So I guess the point I'm trying to make here, and the point that Eddington was trying to make in that quote there, is that he didn't have a means of setting his relationship up and down vertically, exactly, very precisely. But once you pick a normalization, it went through the points very closely. This plot also includes not just giant stars, but it also included the back then main sequence stars, those like our sun that fuse hydrogen to helium in that very first stage of their life, were called dwarf stars. These were included in this study, and they fell on the same fit as the giant stars did. And this was really surprising to him. And of course, that suggested him to a universal relationship, predicting luminosity from mass. And from that, of course, he concluded that his assumptions regarding the ideal gas nature of giant stars must also extend to the much smaller, denser main sequence stars. Again, for reasons he didn't fully understand, not at that time. In this plot here, I've essentially extended his model, which is shown in the blue curve. We're plotting the luminosity of the star in units of our sun's luminosity on powers of 10 on the vertical axis, and then the mass of the star in units of our sun's mass. So you see 1, 10, 100 on the horizontal axis. The blue curve is his relationship, and the red dash curve has a slope of, it's L proportional to m cubed, which was the main finding. Remember, back to his relationship back here. Over here towards the, on the right-hand side, we see the star's luminosity scales roughly as the star's mass cubed, because it's sort of one of the relationships there. And so that finding applies sort of in the middle of the diagram there, where I've noted that right around 10 solar masses and about 10,000 times the luminosity of our sun. As you go to lower masses than 10 solar masses, those stars have lower average temperatures and higher densities. And so their gas opacities are much higher. And so they're much more effective at blocking the flow, slowing the flow of radiative energy through the star. And so they're less luminous than you otherwise would predict from the L proportional to m cubed relationship. And you can see that relationship becomes much more steep in mass. As you go to higher masses than 10 solar masses or so, the importance of radiation pressure at those higher masses means that the average temperature in the star rises more slowly with increasing mass, and with the result that the star's luminosity rises more slowly with increasing mass. In those high mass stars, their gas opacities are about as low as they can be, because the temperatures are high and their densities are low. At this point, I want to point out that you haven't seen a single bit of discussion, other than the mention of energy balance, a single discussion about hydrogen fusion of any kind, or nuclear physics. And that's quite purpose, because it's utterly irrelevant to the star's luminosity. All right, so in fact, the power produced by fusion in a star is actually set by the star's luminosity, not the other way around, which is something which was somehow been muddled and befuddled. So many introductory and public education outlets in astronomy for a number of years now. Oops, let's see. This is a nice little quote from Arthur about his support of the idea that stars, most of them, are in energy balance for the fusion of hydrogen into helium. He said, "The helium which we must handle must have been put together at some point in time, in some place. We do not argue with the critic who urges that the stars are not hot enough for this process. We tell him to go and find a hotter place." So Arthur, being a Quaker, was very polite in his suggestion that someone go find some place hotter than the center of a star. So there is, of course, controversy about Arthur's and a few others proposing that stars were in energy balance through the production of energy from nuclear fusion. The problem was that Arthur's models that were telling him the temperatures of the centers of stars were 10, 20 million degrees were too low, according to classical physics, to explain the process by which fusion of hydrogen into helium can possibly take place. And that's because, of course, that hydrogen consists of protons, and protons are positively charged. They both have the same charge. And so putting two protons together involves a repulsive electromagnetic force. And so two protons, unless the temperature is really, really high, maybe 1,000 times higher than the 10 to 20 million kelvins that Arthur was calculating, unless it was much, much higher than that, there was no way that classically two protons could come close enough for the strong nuclear force to bind them together. And of course, Arthur didn't know how it worked, but he says this is just too good of a answer not to be the right one. And of course, it was the findings of quantum mechanics that the things we think of as particles really aren't particles, but exist as waves of probability filling all of space. And so two protons can easily find themselves bound together under the strong nuclear force by tunneling through the repulsive electric barrier. Might wonder about the significance of the energy balance issue, and that is when the star is in energy balance, that is the energy produced per second from fusion is matching the star's luminosity. Those stars evolve much more slowly, by about a factor of 400, than otherwise would happen if they were out of energy balance and simply allowed to undergo gravitational contraction. And of course, that was the whole issue at the turn of the 20th century, that people turned away from the contraction hypothesis. But it turns out that this gravitational contraction phase, while it's not important in the lives of most of a star's existence, in their first stage of existence as a protostar, before they start fusing hydrogen and helium, when they're initially a much larger, cooler sphere of gas, they do undergo contraction. And of course, it's this process by which the conversion of potential energy of gravity into kinetic energy to particles, by which the temperature goes up and the stars become hot enough to achieve energy balance through nuclear fusion. And once that process by which the energy produced by hydrogen fusion produces per second matches the star's luminosity, then the contraction of the star stops and we have a full-fledged star that's born. Returning to the same quantities here, I'll turn on its side. In this case, now showing the ratio of the radiation pressure to the gas pressure along the vertical axis in powers of 10 again. So the value 1 there is marked with the horizontal dashed line, and then going downward a 10th, and then 100th and 1,000th, and then going above 10 times. And then along the horizontal axis, the mass of the star in units of the mass of the sun, 0.1, 1, 10, and so on. We show this relationship again, indicating that as the stars of that are more massive have larger ratios of radiation to gas pressure. But the vast majority of stars that have masses between 1/10 the mass of our sun and 10 times the mass of the sun, the vast majority of stars that have those masses, which is most of the stars in the galaxy, have ratios that are smaller than a few percent or even a fraction of a percent. So even in the time of Eddington, it was understood that radiation pressure was a minority partner with gas pressure in supporting most stars against the force of gravity. And in fact, it's in stars that are massive enough such that radiation pressure starts becoming an equal partner with gas pressure, that gravity begins to lose its grip on the star. And it's this which actually sets a maximum mass for stars. So the presence of radiation pressure is not so much a source of pressure that supports the star against gravity, it ends up being a disruptor of the star and sets a maximum mass the stars may have. I don't know as to where or how the idea arose that stars are supported by photon pressure, radiation pressure against gravity, but it is ubiquitous. NASA websites, educational outlets, some, not all, some introductory textbooks and so on. It's out there. I don't know where it came from, but it's out there. But it says ubiquitous as it is wrong. So this Eddington luminosity, again, he didn't name this for himself. It was granted this in honor of him. Photons impart a momentum on matter upon interaction through absorption or scattering. And so when you impart momentum, there's an acceleration, and due to that photon pressure, and when that exceeds the local gravitational acceleration within the star will undergo very rapid mass loss. And it's this maximum luminosity called the Eddington luminosity that sets the upper mass limits of stars. And I've indicated that with this approximately what this Eddington ratio of luminosity is in comparison to our sun's luminosity. And you can see that this value scales in proportion to the star's mass. More massive stars can be more luminous, but there's a limit. So a star the mass of our sun, for example, could be no more luminous than about 38,000 times our sun's luminosity. Or a star that's 10 times the mass of our sun can be no more luminous than about 380,000 times our sun's luminosity. And I want to point out that there are some stars that fit this category of being supermassive and super luminous. This is this star cluster R136 in the Large Magellanic Cloud. This, of course, is a JWST image. You can tell from the 6-sided diffraction spikes of that bright star there. There are at least 10 stars in the super star cluster over here, this big blue cluster of stars. There are 10 of them that have masses between 100 and 200 solar masses, and their luminosities range between 1 and 5 million times the sun's luminosity. And in particular, there's a star whose luminosity, I think, is around 5 million and mass about 200 times the mass of our sun. And it's bumping up to it's got a luminosity about 2/3 of this Eddington luminosity. And most of these stars are undergoing substantial mass loss. Well, this page I'm just going to go through really quick here. And there are so many different things that Arthur Eddington contributed to the science of astrophysics. You could spend probably an entire presentation on any one of these. He contributed to the general relativity theory. Of course, he organized the total eclipse expedition in 1919 that showed that space and time curve around massive objects, in this case our sun, and this propelled Einstein's new theory of gravity, space and time, okay, into prominence. And as I said, there are so many areas that he contributed to in a major way. I think another one that was important is that he introduced the English-speaking and English-speaking world of scientists, both in the US and the UK, to this German national. And this was just right after World War I, and not many people in much of Europe or the US were interested in listening to German nationals, but this was one that Arthur put forward as an important, with this new theory of general relativity, and it propelled that theory to prominence and to explain not only curved space, time, and so on, but also it became our major construct for explaining the expanding universe. Arthur died too young of cancer at the age of 61 in 1944. He never married, and his cremated remains were buried with his mother's grave in Cambridge, where he lived for much of his life. and his sister Winifred lived another 10 years, and she's buried in the same grounds. This year, just a few of his main honors. There are, of course, many others as well. And as I mentioned at the beginning of the presentation, his early boyhood home, where they stayed after his father died, still has a plaque dedicated, which I show here in the right-hand side, to Arthur. And in that plaque, they actually carved in to this bronze here Arthur's equation for the luminosity of a star, given its mass. And I want to thank you for your attention, and hopefully you found it somewhat interesting. Thank you.
All right, thank you very much, Kirk. That was fantastic. We do have time for a Q&A. Everyone now has the ability to unmute themselves. So if you'd like to pose a question for Dr. Korista, fire away.
I just wanted to mention that there is a movie that I can't remember if I saw it on Amazon Prime or Netflix or something, called Einstein and Eddington. David Tennant from Doctor Who played Eddington, and Andy Serkis from the Lord of the Rings and King Kong played Einstein. It's actually quite interesting. It's basically Eddington trying to defend a German national on Einstein's theory of general relativity to a bunch of very staid and traditional British scientists who are really giving him a hard time. Obviously, it's been somewhat fictionalized, but as soon as Kirk started talking about his introduction of Einstein to the rest of the world, I immediately hit on that movie, and I just thought I'd mention it. It actually is worth watching, although, as I said, it's somewhat fictionalized. It's rather intriguing. It actually brings in his sister into some of the conversation as well, because I guess he spent a lot of time talking to her about some of the things he was engaged in. So I just wanted to bring that up.
Yep, thank you.
Anybody else?
Yeah, Tom Miller here. In Eddington's 1923 mathematical theory of relativity, there's a comment that, talking about de Sitter theory, he says there's a double explanation of the motion of recession, talking about redshift. First, there's a general tendency to scatter according to an equation. And second is the displacement of the spectral lines due to slowing down of atomic vibrations. Given the first explanation, the general tendency to scatter, I read recently in a paper by Dr. Peacock that Hubble should probably not get credit for the linear redshift. That it should actually be Eddington redshift. Any comment on that?
Well, I think so. Another accolade you could throw in with Eddington that's related to what you're talking about is that he suggested that astronomers go and look for a spectral shift in the absorption lines of Sirius B, which is a white dwarf. So it's about one solar mass object that's been compressed into about the size of the Earth. So it's very dense, maybe 1 million times denser than water. And so that object has a strong enough gravitational field so that general relativity would predict that these spectral lines should be shifted to longer wavelengths by about 30 kilometers a second, or the corresponding amount in wavelength. They went out to make that measurement, and there it was. So this actually confirmed the very strange nature of white dwarfs. We thought we knew that they were super small objects, but some people said, no, I can't be right. We must be missing something. But now we had independent evidence that these are very, very small objects because they showed a significant gravitational redshift. Now, as far as the expanding universe goes, I think Hubble was a discoverer of, well, not by himself, but discoverer of the observational, empirical findings of the expansion of the universe. He didn't necessarily propose a physical understanding of that. That came from general relativity, and of course, as I mentioned in one of my last slide there, Eddington was one of the early researchers that worked through those equations and proposed various possible models of expansion of the universe. So from the point of view that the expansion of the universe has something to do with curved space-time, then yes, then Eddington should have some, I suppose, some recognition in that. Is that it? Is that your question, or address your?
Yeah. I wasn't talking about the star Sirius. I was talking about the nebulae, the redshift of the nebulae, which were actually discovered by Slipher, right, not Hubble.
Well, there were a number of people who, it wasn't a matter of who. I mean, Slipher was one of the first, and there were a few others who were making measurements of the so-called spiral nebulae. That of course became eventually known to be galaxies external to the Milky Way. But Hubble certainly extended that that database. I mean, in his measurements of distances with redshift. So there are multiple contributors to the initial what's called the Hubble relationship. Some have argued that other names might have been added to that name of the relationship rather than just being called the Hubble relationship.
Any other questions? Questions, comments, accolades?
I just want to say I think you did an excellent job. I found it interesting how he had it seems like he had more of an open mind to stuff. Like, I like that, how you introed with that, and how he kind of had the competition, but he was still respectful. I appreciate that in someone. I think that's really cool. That he wasn't like pushy, but he was pushy enough,
Right.
with his thoughts.
Yeah, he had to endure a lot of criticism. Sometimes just in referees' reports where you turn down papers, but sometimes out in public, sometimes in written correspondences and so on. And of course, Jeans would oftentimes go public with his criticisms, and he didn't really pull very many punches.
Right.
Eddington, being the junior, just sort of had to absorb them as much but still, from my readings anyway, he did all he could to hold up his end of the arguments. There are some things that it was true. He didn't have any evidence that, for example, what the state of the star in the interior was. He didn't have evidence. We didn't know yet exactly what the composition of the star was. It was kind of an open parameter. And yet he set these little details aside and pursued the larger lines of evidence that gave him a bigger picture, sort of a broader view of how stars are behaving in terms of their properties, how their luminosity scales with their mass. And as I think I mentioned in that diagram where he laid his model over the data, he couldn't get an absolute. He couldn't a priori say, well, this is my fit with absolute values in luminosity, but he could, with some uncertainty, slide up and down,
Right.
And for some normalization, and actually lay on top of the measurements of the day. And people like Jean said, well, this must be a coincidence or an accident of your mistakes. And whereas Eddington argued, no, I don't think so. I think there's something here. But he had to endure quite. I didn't actually. That's one of the things I didn't know about Eddington. That how much flack he took for his approach to things.
Well,
because actually, the way he describes the way he pursued science is not very different from the way we think about pursuing science today. So it sounded strange. Like, well, wait a minute, why is he criticized for this?
Right.
But back then it was very different. And Sir James Jeans was a giant in the physical sciences of the day, and he was the field marshal, moving the science forward in this very staid, incremental, step by step, only go from what we know kind of thing, and so it was a battle.
There is one question in the chat, Kirk. Are there
Okay.
any books you would recommend? I assume on Dr. Eddington himself.
I can. I don't have it written down. I mean, there's a nice biography out there. I didn't write it down though, but I can provide one. But there's enough. Hold just 1 second though. I might have one in a PDF file.
Okay.
Let me.
Well, if
I think
anybody else,
might be easier. Maybe if I provide that, maybe post meeting, and maybe we
Sure.
can post it someplace.
or yeah, or you could throw it in the chat later, and
I'll throw it in the chat. Yep.
all right.
Okay. Yeah, the answer is yes. I just don't have them in front of me here. So
We could try to put it in the minutes too. All right. Any other questions?
It was a great talk, Kirk. And I do appreciate the equations. The math
okay.
just seems to work in my head. So, having you put those in, I really did appreciate those. So I like them a lot.
I
Thanks.
try to give English, everyday translation as best I can to go with them, but I know some people like to see them as well.
Yeah.
Or know that we have a quantitative way of describing things.
Thank you.
All righty. And I'll end here by saying Arthur Eddington and I have the same middle name too, so I enjoy that. All right, and I want to thank Kirk for giving his whatevereth presentation. I'm sure it's quite a few. And then Kirk mentioned this was his first Zoom talk, but also I wanted to thank Kirk for putting a little extra effort into putting this talk together, because he meant to do it all last weekend, but he couldn't because he didn't have any power because of the great ice storm of 2023. And so that's the first thing I wanted to mention as we jump into the open forum portion of the meeting here, but I'll start with my president's report. So I already mentioned from the ice storm we got last Wednesday of last week. I think it was Wednesday.
Wednesday and Thursday.
I was the lucky one. I was one of the lucky ones. I didn't lose any power, but I lost basically every service Spectrum had to offer. I lost cable, phone, and internet. I didn't mind the phone because all I get is freaking telemarketer calls anyway. But internet got me a little on the shaky side. I thought about committing myself to the state hospital just in hopes they had internet access, but I never did look into that. So I managed to fare the ice storm really well, but it was really surprising. I looked, the best view from my window, from my front living room window, is like west down the road. And you look down the road, I didn't see any damage, but if you look east, and definitely if you drive down there, it was just ripped to hell, or I should say a hotter place, right, Kirk? So, there was one house here on the corner of Borges Drive in Casper, where I live. Like the entire yard was full of branches that just got ripped off trees, and you just drive around. And some places around here were just decimated. So, how did others fare in the Great Ice Storm? Did you lose any trees? Did you get any damage, or lose any toes because you didn't have power?
We went 98 hours without power. And,
oh wow!
And our Spectrum line collapsed almost immediately because of the ice. So after it started melting off Thursday afternoon, I just grabbed my ladder and pulled it from the roadbed and rehung it on my eaves. And when power came back on at 9:20 on Sunday, everything popped on and everything was working from that point on. But that was just over 4 days without power. It was pretty chilly. Bathroom temperature on the floor was about 48 degrees, which was a little bit cold. And if it wasn't for my daughter and son-in-law, they loaned us their gas generator, you wouldn't be listening to me because we've been frozen to death in my living room. So we had a pretty comfortable living room, but the rest of the house was in deep freeze. So And I live in Westwood on the northwest side of Kalamazoo, and we had chunks of trees down everywhere. We were one of the last places in this area to get power back. So we got tree branches and piles of it all over the planet. So I was hoping nobody would be quite as bad as we were, but I've seen other places west of Kalamazoo in which big stuff came down. So we got lucky.
Anybody
There've
else
been
want to
some
mention
dark
their
skies
experience?
down there too.
Well, it's cloudy anyway, so.
Well, I think it was Friday and Saturday night. The skies were gorgeously dark because we didn't have any light. You know, there was nothing south of us. And I went outside because it was cold. But man, Orion, it was just gorgeous. And Sirius was, I've never seen it that bright since the days of our making crop circles at Mumbauer's parents' house. So it was pretty impressive. But we had a couple days of that, and then the clouds came back.
Okay, comments like it was okay here in Phoenix, and you had the job out most night. Again, keep that stuff to yourself. That's just kind of rubbing it in. That doesn't show much sensitivity for those of us in the froze zone here, the ice zone.
Well, I did hear yesterday that it was snowing at JPL.
Wow. Yep, they got some snow in Southern California, I heard. So the weather's just all out of whack. All right, so let's move on here. I wanted to be sure to thank both Jim Bradshaw and Don Stillwell for volunteering at Family Science Night at Hastings Public Library on February 8th. If you looked at the newsletter, you saw a short report and a couple of pictures from their experience there. So Don, thanks a lot. Did you want to mention anything about doing that outreach there?
Just wanted to say that it was pretty busy whole time. That was Jim's first time helping out. He enjoyed it. I particularly liked the kid with the NASA sweatshirt, and said specifically his dream was to work for NASA one day. So that was fun to see a kid that's going to help us get into outer space one day, hopefully.
Who knows? All right, and speaking of outreach, in a recent conversation with the Nature Center, that reminded us that the Maple Sugar Festival is at the Kalamazoo Nature Center on March 11th. That means we usually, we can't go to the place to do any work or anything. But if the skies are decent, maybe even if it's cloudy, but preferably if it's clear, I'm hoping to head out there that day to open up the observatory, maybe do a little solar observing just so people can see the telescope and stuff during the day. Usually when people are there, they can only see it at night. But we want to get a little more exposure for the observatory. But since it will be the daytime, the place needs to be cleaned before we let people in there, at least during daylight. Those that have been out there at night a little bit to say, look at the comet, they didn't notice. But if you go out there during the day right now, the place is a mess. There's just cobwebs everywhere, dead bugs. So maybe, probably not this weekend now because of the weather, but maybe next weekend, I might head out there real quick to try to clean the place up a little bit. So I might put out a little email for help about that. So if anyone's interested in going out there and helping me at least clean the interior a little bit, you can let me know. But yeah, the place is pretty filthy with dead bugs, cobwebs, just stuff people track in. So it looks pretty horrible. But odds are it'll be cloudy and we can't show people stuff in the observatory anyway. But if it's not raining, I still might go out there just to open the place up for a while, just so people can see the telescope, pass out some brochures and stuff like that. And a quick membership update. This will be the last one for a while. Tomorrow's it. Tomorrow's the deadline. I'm going to purge the membership list of those that have not renewed their membership and told me they're going to renew tomorrow. So if you are one of those handful of members that still need to renew your membership, you better either tell me you're going to renew or renew. And if you did tell me that you're going to renew, but haven't renewed yet, just probably by the 1st of June, I'm just going to take you off. I'm not going to say anything. Just one day you'll be gone, and whoop, that'll be it. So we can't keep you on the membership list forever. You got to pay your dues like everybody else. And hopefully, 165 of you recently received your new membership card in the mail. So I see at least one thumbs up there from Sinclair. So thanks to the board for helping me stuff 165 membership cards into envelopes. That was a lot of fun. And of course, I'll bring this up again next month, but we're getting toward a month away or so. But in 1 month, let's see if I can share it here. We'll just share the screen. And a little over a month, we're going to begin another season of public observing sessions at the Kalamazoo Nature Center. You can scroll down the public observing session page here. I'll do so slowly. I don't want it to fly by, so someone throws up or something. But here's the full schedule. So, of course, our first session, weather permitting, is on April 15th, which I think is still tax day, or I think they may have changed it. But, you know, we always do 2 a month from April to October. If we're lucky, we'll pull off about half of these, but last year we pulled off a little more than half. So we need people to bring out telescopes, because for a lot of the sessions last year, it was basically sometimes just me, but usually me and David Parks. So we definitely need you know, people to get back to normal, because one problem we never had was people bringing out telescopes. But since the pandemic, we've had a little issue of people bringing telescopes out. So, you know, we need members to do that. I realize the entire membership can't do it. That would get a little crowded too, but we need roughly half a dozen, which isn't too much to ask for. And so, I don't think Jim Kurtz is here, but I know, for example, Jim Kurtz, his telescope is now in his observatory at Arizona Sky Village. So, but remember, we have a very nice telescope in our observatory. Usually I use it, but we can take turns. So if you don't have a telescope you can bring out, but want to, you know, maybe share stuff with people, just kind of say, you know, could I use our observatory that night? And I could bring out my own stuff that night instead. So there's always an option. You could always use the Owl Observatory telescope if you don't have one of your own to bring out. But we need people to bring telescopes out, so poor Richard doesn't have a nervous breakdown and is doing this stuff all by himself, because that's not the way it's supposed to be. So that's it for the President's Report this month. Let's move on to observing reports. We had clear skies on March 1st, so I'm assuming many of you saw the nice conjunction of Venus and Jupiter, only half a degree apart. Anybody want to give a report?
It was spectacular.
That's short but sweet.
It was neat.
It was neat. Okay. It was neat. That has one more word than Sinclair's report. No, that's the same. He said it was spectacular. Okay, so that's the same. 3 words. Anybody?
Yeah, but he had more
syllables.
Yeah.
No, it was a good binocular object. I had my 7x50s out with my girls and stuff, and just good separation. You can see the Jupiter moons. I mean, they really enjoyed it. I mean, it's not, you know, a Hubble image, but it was pretty cool to see.
Pete, you're pushing 50. You better trade down for some 10x50s there, old man.
Got my reading glasses.
Yeah, I took my camera down to Asylum Lake and got a nice shot down there.
We saw it. Yeah, that was great, Eric. Cool. I figured we could share some pictures at the Astro Sig meeting. I won't share any, but I drove out to Richland Township Park just because it's wide open there. They got a nice tree horizon instead of streetlights around my place, and now I have the terrible LED streetlights that I need to write to the township about and swear at them. Tell them to go to a hotter place.
On the neighborhood discussions were all about UFOs and drones flying around, and one of them said, you know, we were looking in the west, and then They seemed to be coming at us. And then we went away, but after 10, they just disappeared.
I know those are those reports are from what you call stupid people.
I had several Facebook messages asking me, "What is that?" We know you would know. People wanted me to tell them what it was because they figured I'd know.
They apparently don't watch the news. They mentioned the conjunction in the news. So that was nice.
Yeah.
I did. I wanted to finish up here as I did take some pictures, and I'm not going to share them now. But if you want to see them, you can go to either our Facebook page or Twitter or Instagram, because I put my pictures on there. And if you did take pictures, please share them on the Facebook group page for the Kalamazoo Astronomical Society. We're starting to get more activity in the Facebook group page. So if you have any pictures to share, please post them on there. Let's get a discussion going, get people chatting. Anybody else see the conjunction? Want to give a report? Jeremiah? Yeah, I'll have to, yeah.
Well, I saw it, but I was just like there was so much hecticness I couldn't even do anything, so I just kind of like gave up on it. But I did I tried to take a picture with my phone, but it was horrible. Yours were so much better. I was like, dude, I'm not even gonna post that. Like, it was just yours kicked mine out of the water. So
I was hoping to get out there a little earlier to get it more in twilight, but I couldn't make it. There's again, yeah, too much going on.
I like the look of yours though. They look clean.
Yeah, it was hard processing out the light pollution from Kalamazoo, because on the left side of the photo there's this big dome where Kalamazoo is. So I tried to get rid of that as best I could.
No, they were good.
And of course, Alan Dyer has some really nice scenic photos. I hate that guy.
I hate that guy.
Any other non-Venus Jupiter observing reports? We have had some clear skies, Pete.
Yeah, I took the wife and girls out to see the Starlink train that went overhead, I think a week ago. That was pretty cool. I mean, they don't bother my pictures really, but it was pretty neat to see and answer questions about how big they are, which isn't really, I mean, they're not really big, but they were pretty bright. So get used to seeing those as they launch more and more.
Yep. I know Jack Price mentioned he saw some right after our board meeting.
Yeah, I was surprised. Usually I only thought you could see them like hours after launch or within a day, and this was 2 days after launch. So they were still.
Well, you'll see more because the Chinese now are convinced that that's some kind of conspiracy, and they're going to launch their own series of Starlink. So,
but Amazon's launching. They just have a contract now. They got approved by whoever approves them. They're gonna put up there a couple thousand.
Yep, our next fundraiser is going to have to be an anti-satellite laser. Start shooting them things down.
There you go. Or that, or advertising. You could have like satellites linked together to make the Pepsi logo or something.
Yeah, being in digital advertising, there's some crazy stuff that we can order up. Even like drones, where you can order up to 1,000 drones into a big pattern, and they'll do a whole show.
Oh yeah, and then we don't need
crazy.
Don't need nighttime things like stars and planets.
Yeah.
That's it.
So I have another observing report. It's a very small one.
Great.
But Sunday, the 26th, was such a beautiful, gorgeous, sunny day. I went outside, and with my binoculars, I saw sunspot 3234.
Oh, great. Yeah, I've been meaning to ask the membership about those binoculars, because the smaller set, they're only like, what, $20, $25, and how many people would buy those from the KAS if we got some of those to sell for the eclipse? Well, we'll have to take a poll on that when we're in person. It's harder on Zoom, but so or you could just put it in the chat or email me always, So I figured maybe we could try to get maybe a couple dozen of those and just put them on the website and sell them and take them to events where we sell eclipse shades.
Karen and I got a pair of the little lunts for the 2017 eclipse.
Yeah,
and they're pretty sweet. I mean, they're not real powerful, but they're pretty sweet. And for the size of the sun in it, it's not bad. I've never looked at the bigger ones, so I don't know what that would look like.
Yeah, I have the bigger ones. I won them. I got them for free. I won a contest from Lunt. Both Jim and I did at the same time, and we're like, like half a town away from each other, and we both won at the same time. The one thing I've discovered about the sinoculars is when you look through them, it is really hard to find the sun because you can't see anything.
What's the eye relief on those?
Off the top of my head, I don't know. Maybe if we get a break here, I could run out and grab them. They're in the next room, but I don't have them handy.
I have both sizes now, and I thought I'd write an article comparing them for the next newsletter.
Oh, there you go. Great.
Good timing. Yeah, definitely.
Yeah. All righty. So if there are no more observing reports, we'll move on here. Going once.
I was actually wondering if anybody saw the aurora on Sunday. I did not see it, but I heard it was visible.
Yes, there was aurora. I did see there's an astrophotographer in Delton that posted a nice photo of it near a lake, which I assume he lives near. So it was visible from our area, but I didn't think it'd be visible, so I didn't bother going out to an open area to try to take pictures. But I did see that nice photo from Delton, which I could probably find if I tried.
Flowers.
Yeah. All right, so let's go ahead and move on. Usually I have some astronomical news and events prepared in case no one mentions anything, but I've been a little preoccupied with something I'll mention here shortly. But does anyone else have any astronomical news and events? This month I got nothing.
NEAF's on.
What's that, Pete?
NEAF. That's actually going to happen this year.
Oh yeah.
Yeah.
Is Scott McFarland on? Because I thought I saw him on. Yes, there's Scott McFarland. I don't know if Scott can unmute himself and tell us if he's going to go to NEAF or not. I know he tried to go last year, but of course they canceled it.
Yeah, I plan on going. Scotty and my brother Mike and I think are driving down.
Okay, cool.
Yeah, I'm pretty sure I'm going to.
Oh, I thought you weren't going to go.
Nope, I moved my schedule around. I'm gonna probably go to the imaging conference too, the couple days beforehand.
Oh, I can't go to that. Shoot. NEAF is in New York. It's right on the New York-New Jersey border. You can, usually people stay in New Jersey and drive to Suffern, New York. That's where it is. It's at this community college, Rockland Community College, and it's basically Candyland. If you've never been to NEAF, any type of equipment you've ever imagined or want to imagine or didn't know exist is there. Someday I want to do a NEAF type event here in Kalamazoo that I call GLASS, the Great Lakes Astronomy Super Show, but that's still maybe a few years away. I need to see if we can do that, but that'd be much more reliable to do than a star party because, Michigan.
I'll plant a seed in astrophysics here when I'm there.
Yeah. Well, I already got Planewave. The Planewave said they would participate, but so that's one. Any more astronomical news?
I did want to mention one thing, Richard, that I saw Wednesday night. After I took my pictures of the conjunction, I was going online and looking for some data on it so I could tell some people I knew. And I got on Sky and Telescope's website, and right on the front page of Sky and Telescope was an ad for Kirk's talk tonight.
Really?
Whoa, nice.
Really?
Because I just saw something about Eddington. It's like, wait a minute, that's what we're having. And I scrolled down. It's like, oh, hell.
Okay.
It's us.
I wasn't sure if I submitted it to Sky and Telescope or not because I forget. Like I said, I've been preoccupied lately. Any more news?
I've got notice here from Michiana Star Party. They're going to be meeting from May 19th through the 21st of this year at the TK Lawless Dark Sky Park.
Yep. I've never been there during the day, but I gave a talk at the Michiana Star Party 2019, in fact, right before they couldn't hold the event for a while. And it looks like a pretty good site. I'm still not quite sure, how good the skies are, but they're obviously better than what we have at the Nature Center. So it is a good chance to camp out there. And sometimes they have, they tend to have some nice speakers, except for me. They had me, but I'm the exception to the rule, of course. Any other news? Again, I have not been keeping up lately. I've been busy. Okay, so let's move on. Talk about the event horizon. Next up is an astrophotography SIG meeting. Our guest speaker will be Zolt Levy or Leve. I still got to work on the pronunciation of his last name. He's actually done some processing of James Webb and Hubble Space Telescope images. We'll probably have him back to talk about that at a general meeting sometime, but Zolt will be talking about basically nightscape photography. So if you have a DSLR camera or a mirrorless camera, definitely participate to listen to his presentation and see many of his beautiful landscape images. If I was really more prepared, I would have shared his website real quick, but we'll definitely send out an email about the last astrophotography SIG meeting of the season, because this will be our last meeting until October possibly. So be sure to join us on Friday, March 17th for the astrophotography SIG meeting. It's going to be a good one. This should be a really, really good presentation. And then we're going to have the Messier Marathon at Richland Township Park. Yes.
Richard, I just want to mention, so Zolt and I overlapped. Well, he's been there, of course, all this time, the Space Telescope. I did my second postdoc from 92 to 94. And he was just down the hall from me. He's an instrument scientist, and I was a postdoc on our science project. And I used to go and consult with him on reduction of data and that kind of thing. So, it'd be nice to see him again.
Yeah. Well, we're gonna of course we're gonna have it at Root Hall, but with the way this season has gone for Astrophoto SIG meetings, we just decided to switch entirely to Zoom. And that's the way we might go in the future too. So we're going to be on Zoom for that one, unfortunately. But I got to remember to contact him about that, because he was thinking about coming to do it in person. But we're just going to stick with Zoom for the SIG meetings. All right, as mentioned, we have the Messier Marathon on Saturday, March 18th, weather permitting. That'll be at Richland Township Park. It's a great area if you really want to do a Messier Marathon. If you want to stay all night, that's totally possible at Richland Township Park. They leave the gates open all night, so you can come and go as you please. You don't have to wait for me to let you in, or I'm not going to throw you out to close the gate like at the Nature Center. And if you just want to come and observe for an hour or 2 or 3, you can just do that too. But if you're going to be serious about doing a marathon, we'll try to leave you alone so you can knock off like the Virgo cluster, because that can be a little time consuming. You got to figure out which galaxies which and all that. So when you arrive, if you're really doing a marathon, just let us know and we'll kind of leave you alone until you get to the easy part, and then we'll give you a hard time. All right, next up, Prime Focus is, of course, as usual, the deadline is the 15th of every month. So if you do have any images or reviews or articles that you would like to send, please try to do so by the 15th of the month. And I wanted to see if everyone enjoyed the current issue of Prime Focus, because that one seemed to get a little more rave reviews than usual. So I hope you all enjoyed the current issue of Prime Focus. Everyone actually, or many people actually participated for once. So I got the nice article from Don Stillwell. I got the article from Sinclair. And so the newsletter goes a lot better when people actually contribute. So thanks for checking it out if you have. If you haven't checked out the newsletter yet, please do. That one was a little more effort to put together. And speaking of the newsletter, that's what I have been preoccupied with lately. Not the current newsletter, but old newsletters. So let me share the screen here. Can you see that? How many of you know the significance of this issue?
That would be...
It wouldn't be Don. I hear Don, but Don wouldn't know. I'm sure Sinclair or Mumbauer would.
Trying to read the contents there.
Yeah, that's an old one, man.
This is a special one. This is my first.
That's what I thought.
Oh, okay.
This is the first one. So I haven't talked about this a lot. I've mentioned it a little bit from time to time. It hasn't been exactly a secret, but for a long time during the winters, for I don't know, the past 4 or 5 years, I've been slowly scanning my first set of newsletters from my first run as newsletter editor from 1996 to toward the end of 2001. And this is my first one. that's now been fully restored. So let me see if I can scroll down here. I gotta click on the window.
27 years.
So
Wow.
you can see the format's a little different. My initial text here was really terrible because it looks, if you zoom in, which I'm not going to do, it looks worse when you zoom in. It turned out all blobby. And so you can see the format's a little different, but you know, it hasn't changed a whole lot. So here's a nice article I asked Eric to write for the first issue because I wanted to have something for the first one. This is an old report I did for a class on the Challenger disaster. And so you can see this page looks pretty bleak. Of course, you can go to Writers and ask Pete for telescope advice. Of course, neither he or Writers are still there. There's the treasurer's report. Back then, we had a whole $111.02 in the bank. When I first did this issue, I printed it all out in color, and this page looked terrible because the black ran out. So, but now it looks as intended. And so you can see, and also the significance of this issue is in January. We can go back here. This meeting here on January 5th, this was our very first meeting at the Kalamazoo Area Math and Science Center.
Yep.
So that's why I have the map to Kamsey in here, and you can see they have laser discs and MS-DOS machines. So you can see it's a little dated.
Yeah, it's just a bit.
So I mentioned this because just today I just got done cleaning these up because, of course, scanning is the easy part, but the hard part is to go in and really clean them up. Because one thing I tried to do is I tried to replace the scanned images, which some have looked terrible, with the original images. So like, you know, this I found online, and this is the actual image that I used. But of course, in the scanned version, it looks a lot worse. So so I replaced the scanned version with the cleaner version I found online. So not only have I been scanning these and just removing, you know, kind of making the screen whiter instead of kind of grayish, I've been trying to replace images and really have the issues and the newsletter look as I originally intended. So you can kind of call it the special edition of Prime Focus. But this is the way I meant to do, because, you know, back then, as Sinclair knows, when I, you know, printed these out, because this was the only issue I printed all on my own, but from the February issue going on, I had to go all the way up to the 4th floor of Old Central, meet Mike at Kamsey. We had to photocopy them and fold them and tape them and stamp them and put the labels on. So, but you know, so back then I was a lot more limited in what I could do. You know, I tried sharing pictures of members, but their faces were always blacked out from the photocopies because, you know, you're making like a copy of a copy. And so, so I've been trying to fix as much of this as I can, you know, to just clean them up. And all the original newsletters are now online. I have uploaded them to the website, but there are no links to them. But if you know the way I do the URL, you know, I do the structure of the web page, you can find them. They're all on there now. But eventually, what I'm doing now is I'm going through these again just to see what else I can kind of clean up and replace, you know, what images I can replace with the original color versions. And I'm slowly going to tweak these. But I've already done the first year of Sinclair's newsletters. Those were, in fact, a lot easier to clean up. I'm happy to say. That first issue that I showed you, the January issue, where I printed it out one by one, of course, the print bled through. That took me like pretty much a full afternoon total to clean up, because they were a freaking mess. You know, you could see both sides on one side scan, so it was rough. But
are they in 4K?
Yeah, no, they're not in 4K.
And I don't care if they're your special editions, but Han shot first.
Right. That's right. So as soon as I'm done with these, because I want to, you know, as soon as I get done tweaking my issues, I'll finish up scanning Sinclair's. I'm going to go back and do Mumbauer's year because he was editor in 1995, but The bad part is those booklets. I'm not sure how I'm going to do those. Booklet format does not translate well to PDF style. So I'll see what I can do with those. I'm not quite sure yet. I'll probably just scan them, break them up page by page and do it that way. Because I remember when I first started doing the newsletter, Pete Nundero wanted me to switch to the booklet format that Pete did. And we actually held a vote at the Math and Science Center at one of our first meetings. And I basically got up and said, I don't give a rat's, what you vote. I'm still doing the full page format. And guess what? I won anyway, but it didn't matter because I was doing it the way I was going to do it. I'm not paid. No one pays me. I'll do what I want. I sound like Cartman.
You were the newsletter editor. That was your purview. That's what you're supposed to do. I don't have any idea why he thought. Well, I know why.
So to quote Eric Cartman, whatever, I do what I want. If you're not a South Park fan, you have no idea.
It's just amazing how well you do Cartman.
I respect your authority.
Respect my authority. I should mention, I have this fresh in my head because during the cable outage, I finally watched the DVDs of South Park my niece got for me because I had nothing else to do. so I watched like the first 2 seasons, like 1.5 seasons of South Park. So I have those episodes fresh in my head.
Yeah, in hindsight, it was crazy to do booklet form, stapling them, and
yeah.
What was I thinking?
Yeah, it looks nice, but yeah, for converting to PDF, which we had no clue of back then. Yeah,
well, that's awesome.
It'll be fun.
Fill in that archive and just keep that history going again. So that's really amazing.
And I do have several from the almost a complete set from the 70s and 80s. There is a gap in the early 90s, and I'm not even sure those are worth filling because I saw some of Bill's newsletters from the early 90s, and they're just not good.
Hey, early 90s, man.
Yeah. So
give a break.
And I don't have those anyway, so I'll have to see if anybody else has them, like Mark Miller. I don't know if Eric has them, but yeah, eventually I'll get to those as well. The ones from the 80s will be hard because they were done on a mimeograph machine, and they're really faded, and so those are going to take extra restoration to even make them readable. And plus, the really hard thing about some of those newsletters in the 70s and 80s, if you look at them, you can't tell when they were, what month they were. You have to really look through them to figure out, because they don't put the month and year on the pages anywhere. So sometimes it's hard to tell what freaking month and year it was. So I'm looking forward to going through those. I only work on these in the winter because I'm not doing this in the summer, and so I'll get back to that. I see a smile on Eric's face. So Eric, did you have something to share?
Those 70s and 80s ones that were done in Mike Potter's basement with the mimeograph machine. Ooh, did those smell good?
Uh-oh. Uh-oh. Were there some high nights in the basement back then?
Oh, yeah.
Oh, boy. Uh-oh. Uh-oh. Eric inhaled. All right, moving on. Anybody else have anything else to mention?
Hey, Richard.
Yeah.
Were we still thinking about having a last remote observing session on the 11th?
I haven't thought that far ahead because I got to tell you, I've been completely obsessed with trying to make progress on this newsletter thing. I haven't been paying attention to anything else.
Well, because it's next weekend.
Yeah, I think the moon will still be in the way. What I was thinking is if we get clouded out for the marathon, and if it's clear out west, then we might do an online session instead of the Messier Marathon. I got to tell you, speaking of the remote scope, I wasn't going to mention it, but the weather throughout February out there has been terrible. So if you read the newsletter, you know that after Patton either dies or decides to sell the place, I think we'll just sell the telescope because, when we first got into this, we were told and, read that there were like 330 clear nights a year out there. Maybe there was pre-climate change, but now the climate has gotten so messed up, it's cloudier out. It's still better than here, they have much longer strings of clear skies out there than we do here, and it's much drier, much darker. But boy, I've never seen such a worse month out there in all the years we've been watching the weather. It's been terrible. If you looked at the all-sky camera last night, that thing was totally encased in snow. All you saw was this bright thing where the moon was, with ice crystals being illuminated around it. It was bad. So the weather's out there has been terrible, but hopefully it'll get better. We can start imaging again. And I was going to mention the one thing I wanted to mention is I don't know. Let me go back to the browser here. Let me open up my email. You can see all the wonderful email I get. Don't look at my Discover information there. You'll try to steal my credit card. But I don't know if Mumbauer got this email. You can enter the lottery to purchase one of their Astrophysics 110 refractors. And I was thinking, gee, if we sell the Takahashi and maybe even the Moonlight focuser we just got, we could switch off to an astrophysics refractor as opposed to the Takahashi. That would certainly solve our tilt issues. Because I think our focuser is robust enough to this focuser is robust enough to support the camera. But eventually, as Pete and I were talking, we might actually want to sell the cameras sooner rather than later, and upgrade or kind of up/downgrade to CMOS versions. You know, get something QHY or something. So that's also something to consider.
I did get on the list for that scope.
Well, I figured since they have a lottery, if we decide to do this, try to enter the lottery and buy one for the remote telescope, several of us can enter, and whoever wins can purchase it for the club, and of course we'll reimburse you eventually.
Actually, I saw the announcement of those new quote unquote medium format cameras. And I thought that's what we should replace. Get ourselves some medium format kit cameras out there.
I don't think we can afford it.
Yeah, they were pretty pricey.
Yeah, I know the Takahashi couldn't handle it the way it is now if we ever get the tilt right. Of course, we haven't been able to work on it for a while because the weather has been really bad out. I mean, really bad. You know, the whole Southwest is screwed up right now. You can see that in California where it's snowing. It snowed on the Hollywood sign. So yeah, the weather's been rough. All right, is there anything else anybody wanted to mention? All right, preview next month. We have Dr. Kyle Cudworth, who Eric met when he was at Yerkes Observatory, because Dr. Cudworth is the former director of Yerkes Observatory. Now he's emeritus with the University of Chicago, and he'll be presenting via Zoom, but we are still hoping to meet at CAMSI. I was even prepared to show our new eclipse poster. This is just the electronic version, but I went out and bought a frame for our new 2024 eclipse poster that we were going to display at meetings and stuff going forward. And so we'll be at CAMSI, and his presentation will be the Tales and Tales of Star Clusters. So that'll be a really, really great presentation on clusters. And I presume, looks like he may have checked out on us. Jeremiah was supposed to provide snacks this month. I presume he'll just switch over to the April meeting. I did ask him about that, but he did not respond. So if there's nothing else, we'll go ahead and officially adjourn. Thank you for joining us for the March General Meeting of the Kalamazoo Astronomical Society.